I will begin with some general facts about what I will be discussing, and please feel free to interrupt me during the discussion. And also, in case you don't hear, because I don't know how efficient this device is, you will tell me, okay, if you want me to speak more louder. So let me start with, first of all, everything I will be discussing, it's a project that has taken some time now, at least 10 years. And it is joined with Giorgio Fusco. So my collaborator is Giorgio Fusco. So I want to start with some basics and introduce the problem I will be discussing and introduce the notation. So I will be discussing the equation Laplacian u minus the grad of w of u equals 0. And my notation is a little bit unusual. By that I mean what most of you would use for this is this. Okay, and I want to think of it as a column. So I want to discuss this system, so I will be particularly interested in entire solutions. So I will be interested mostly in solutions from Rn to Rm. I will be referring to W as the potential. Actually, physically, minus W is the potential energy, not W. And let me start with some basic assumptions about W. W will be non-negative, so really it will be bounded from below. That's what we need. Regularity is not an issue, so take it to be regular, and I will specify how regular in certain cases, but regularity is not an issue here. And so the zero set of W is important in this discussion, and depending on whether it is connected or disconnected. So the connectedness of the zero set is an important issue. Now, let's observe that we have two extreme cases. One extreme case is, of course, when n equals 1 and m is general. And in this case, what you have here is a Hamiltonian system of ODEs. I will be referring eventually to the solutions of this, to some special solutions of these that connect minima as either connections or actually geodesics. They are actual geodesics. So the other extreme case is certainly you can take m equals 1 and then take n to be general. And this is the scalar problem, which by itself is very interesting and has been studied a lot. So these are the two extreme cases. I will not be interested in the main body of the talk in general solutions, but in bounded solutions. But I want to begin with some basics without making any hypothesis about the solutions and without making any hypothesis about boundedness and things like that. So let me start just with this very basic facts first. So let's start. The first most important fact about this system is that it is variational. So this is the Euler-Lagrange system, the Euler-Lagrange equation of this energy. Let me introduce a notation. So this, I introduce this notation for what we normally call energy, but actually it's the free energy of physically this is what it is, the free energy. So the Euler-Lagrange equation is this. This is the most important fact. Now, another important fact is that this can be written as a divergence-free condition. So there is an energy stress tensor. So let me, this notation means partial with respect to xi. This is inner product with partial with respect to xj. And this multiplies energy density. Okay, then you can do a calculation, and you will discover that the divergence of T is equal to this matrix times this. And therefore, we have this fact. This is an important fact. Physicists know they have the formalism for a large class that includes also this particular one. For example, if you go to Landau-Lifshitz, that they will tell you it is known that it can be written as a divergence-free condition. In our community, this certainly is known in special cases by the experts. Okay, so it's not something surprising. But as soon as you have this, you can derive certain consequences of this. And I want to just to mention some consequences of this. So we have these two facts. These are important facts. So let's derive some consequences. The first immediate consequence, essential immediate consequence, is a monotonicity formula. So you have the monotonicity formula. This is a ball. Doesn't matter where you center it because this is translation invariant. So you have this fact. Okay, this is the monotonicity formula that corresponds to harmonic maps. We will see later that I will specialize things and I will be discussing the situation that is the analog of minimal surfaces, and the other monotonicity formula would be n minus 1. So you have this fact. This is an easy fact. It's a consequence. And you have the other consequences that are useful. For example, you get Pohozaev's identities. You get what Gui called Hamiltonian identities. That is certain, because you have the divergence theorem, you can integrate it over rectangles, you know, something at infinity, and then you can connect the value on the lower bottom to the value on the upper bottom. Okay, so you have, it gives you a control like this, provided you know asymptotic information on part of the boundary, which normally is at infinity. So this is a useful fact. So let me record this very quickly. You get Pohozaev. This is how normally people think in PDEs in order to derive identities. Or you get Hamiltonian identities. For example, you can derive. And Gui was the first to derive Hamiltonian identities using Pohozaev type of arguments, etc. So you get this. Now, as a consequence of the monotonicity formula, you get a Liouville information at infinity. In my talk, I'm interested at infinity. So the cones I'm thinking about, as you will see later, is at infinity. I'm not interested at a point, but at infinity. So for example, from this, you get another consequence would be the following. You will get that if you have a non-trivial solution, if the solution is non-trivial, then it has to grow at least like this, okay, if n is more than 3. And with a variant argument, it has to grow more than logarithmically if n equals 2. So these are experts that know that as soon as you have especially in geometric analysis, that if you have a divergence-free formulation, you have certain consequences. For example, monotonicity formula, and then from this, it's an exercise simple exercise to get this. Now, a consequence of this is the following, which is important. So let me just write down a very special case. So the consequence is that so let's write it as follows. If the free energy over the whole space is finite, then the solution is trivial. So you get this consequence. So what's the implication of this? The implication of this is that you cannot, if you want to construct solutions to get existence, you cannot just minimize the functional. This is true for n greater or equal to 2, is not true for n equals 2. So this is true for n more than 2. The action, if n equals 1, is always finite. So the abstraction that you get, and it indicates the difficulty, is that if you want to get solutions to the whole space to the equation, non-trivial solutions, then the way you will do is that you will have a ball, you will minimize over the ball, you will get something, and you hope to pass to the limit, okay? And to get something non-trivial. But clearly, you have to be very careful passing to the limit so you don't lose it and you don't get a trivial solution. So this is the first abstraction in existence, the fact that the energy is infinite for non-trivial solutions. So you cannot really use immediately the direct method.
For n equal to 2, it is correct?
What?
No, you said that for n equal to 2, it was not true.
No, the logarithmic.
So for instance,
Yeah. So this is true for n greater than equal to 2, but it is not true for n equals 1. For n equals 1, if you have a geodesic, the geodesic has finite energy, is non-trivial, and so on. So for n equals 1 is not true, but it is for the other dimension. Okay, so that's to begin with some general facts. Let me see if I told you everything I wanted to. I think more or less I did. Okay, so now I'm going to particularize things, and let's see. So I want also the other to go up. That I don't know how to do. There must be a way. So I cannot get the other up at the same time that the one is going down. But later I can do this now?
no, not at all.
I see. Okay. 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 Now, let's particularize things. So now I want to discuss what I will call phase transition potentials. And I want to discuss minimal solutions. And I will be interested in bounded solutions. This is what we will be interested, just in bounded solutions. So let me say something general to sort of give you the context. I'm sure Tonegawa has given a series of lectures of relating the reaction diffusion system to the sharp interface system. So you know there is a diffused interface if you scale it with epsilon that we have seen in previous talks, and the sharp problem. This is an analogy that also can be quantified, but the kind of theorems you want to prove in general do not reduce just to the geometric problem. So there is some rigidity, but it is rigidity in the PD that mimics the rigidity of a Bernstein type of result, but it is not just absolute reduction to the limiting problem. But this is the inspiration. So I'm suggesting the Georgia, things like that you know, most of you know very well, these things. So now what I mean by phase transition W's. By phase transition W's, I mean I take now the zero set to be discrete. As I said, totally disconnected. This has nothing to do with the dimension. Now, observe the following, that in the scalar case, it doesn't matter. All W's are the same. But in the vector case, you have fundamentally different W's. So the kind of W that I want to consider is a W with a finite number of minima. And depending on the connectedness versus the disconnectedness, there is, of course, the other prototypical W that we all know, a so-called Ginzburg-Landau W, where the zero set is S1 and so on. So I don't want to discuss this, which is like a harmonic map problem, and this is more geometric problem. So this is the problem I want to discuss. For this kind of W's, the energy concentrates differently if you do the epsilon scaling here, then it concentrates there. So that's the first general remark I want to do. So this refers to this. Now, what about this? Minimal solutions are exactly like minimal surfaces. They minimize subject to their Dirichlet conditions. Okay, so we write it down. So what does it mean? Because, of course, we have the obstruction with the infinite free energy. Then what we want to do is that we take omega to be open bounded. So the energy makes sense. And then I say U is minimal if for every V I get more for U plus V having the same boundary conditions. So for every V with compact support in omega. So this is minimal. So we have to be very careful. This is not a local minimum, it's a much stronger condition, it's like a global minimum. So I'm going to restrict myself to this kind of solutions. Why we need, from the phase transition point of view, a order phase parameter? Well, look, if you try to have three phases and you are naive enough, and this is how all of us are at the beginning, and try to model this with a scalar order parameter, this phase will never see this phase, because actually there is no mathematical connection solution which says at minus infinity this plus infinity that. So you need a vector order parameter to do that. So I will be calling this the phases. And what now we have in mind, for example, for a triple well potential, it is good just to suggest things. We will have certain partitions in mind, and we are interested in triple points. We are interested in coexistence. So this cone will be important to us, and I'm going to do others that you are very familiar. So that will be another one, and then finally the cone that also we will need. So a partition meaning here I can put one phase, the second phase, the third phase. A partition here that would be for a 4 well over R3, and I would put here one phase down, I put another here, I put another here, and I put another here. So this is what one has in mind. So one has in mind, if you try to go in the sense of, in the program of de Giorgi, like in the scalar case, where you want to prove that in low dimensions you have a plane, now you want to prove that in low dimensions you have a cone. This is the Bernstein thing that actually there are experts here that have worked on that. I think Frank Morgan in particular was one of the first that proved the theorem of this sort. Actually, Fleming was the first to formulate it like this, the Bernstein theorem. So this is what is in the background. This is the background. Now I want to be more precise. So let me write also the scaling thing that I have been suggesting and so on. So when I say the epsilon problem, at least I should write it once. I mean this. I mean the blowdown. I mean the blowdown. So if you are interested in discussing something at infinity, this means like in new variables. So this is y variables. So where x is y over epsilon, in new variables you study this over the unit ball, and as epsilon goes to 0 at finite y values, this corresponds to what happens at infinity. So this is the kind of thing you have in mind, and this is suggests what I will be discussing. Okay, so now let's be enough of this sort of intuition, and let me state a basic estimate, a very simple estimate, but very basic. By the way, this estimate also holds for this connected zero sets. So the estimate is the following. If I always under this hypothesis, I'm not going to state them and restate them all the time. So this is the basic estimate. I'm interested at infinity. So this already suggests something, but it suggests that you grow like this n minus 1. Proof. The proof is very simple. You use minimality, so I don't have time to describe things precisely, but let me tell you what kind of proof you will do. I mean, you could always do a proof like you put equal to A inside, equal to U outside, and you take a competitor, which is like this, out, and with some non-annulus and of radius, and this is fixed, so that could be r plus 1. So say this is r. I didn't do it well. Okay, so this is r, and this is r plus 1. And then you do an interpolation, an obvious thing. This is a minimum inside. Inside you take it to be a minimum. You compare because of minimality. It's a very simple thing. The volume of this, because it says fixed width, is like r to the n minus 1. You are done. So this is a very basic estimate. Now, the next thing I want to discuss is existence. At least to tell you some things that are known for existence. And let me let's start first, because it's important to take the case n equals 1, and this is what I would call connections or geodesics. So existence, what existence would mean? Suppose I had three minima, A1, A2, A3. An existence of a connection is a solution of the ODE system, which at minus infinity goes here, plus infinity goes there, and you would expect something like that. So that would be three connections. So these are curves in space. You minimize the Hamilton energy, the action, but because of equipartition, because of the fact that in one dimension you have this fact, then this relates to a length functional with a certain weight. So it's like when you do the plateau problem, you start with an area functional and then you go to a Dirichlet energy, and then the two coincide at the minimum. So it is the same kind of idea. So that's why also one calls this geodesics, because this minimizes something like this as well. Because these two functionals coincide because of this equipartition with the Hamilton functional that we started out in this case. Okay? But now we are interested when n is more than 1. So let me state the theorem. Let me state the theorem. I will restrict myself to equivariant solutions because simply they are simpler and simply because nothing is known for general solutions. So it is at this point a necessity. That's all we know. So I will tell you what we know. So equivariant solutions. This means I'm going to introduce the symmetry. And let's be careful since we are stating a theorem. So let me take W to be C2. Let me take W to have exactly what we said. And let me assume that the lim inf at infinity is positive. Let me also take the W to be non-degenerate at the minima. So this is a non-degenerate condition. The linearized problem is okay. You can use it. Now, symmetry. Assume that G is a point reflection group. And I will draw, just to keep in mind things, take the equilateral triangle group, okay, 6 elements, generated by reflections. So reflection group, W invariant, where the reflection in Rm, because we want also to say something in Rn, let's not bother, and for convenience, there is a way to do something even in the other case, but let me take Rn larger than Rm so I can embed the group also in Rn. And I'm assuming, therefore, this for W. So think of a triple well which is symmetric under the symmetries of the equilateral triangle. Okay. Now, an important hypothesis. So far, these are kind of obvious. Important hypothesis, where we are going to place, we have a fundamental group, a fundamental domain. Say this, I choose as my fundamental domain, 60 degrees. I am allowed to place a minimum, a unique minimum in the closure of the fundamental domain. So there exists a unique A, so say A1, in the closure of the fundamental domain. And I'm allowed, I can put it here, and in this case capital N would be 6. I can put it here, capital N will be 3. I can put it here, capital N, the number of minima, would be 1. So let's put it here because it's interesting. Then I look at the stabilizer, that is those G's that this is on the reflection plane. And then so look at the stabilizer of A1. So it is those G's that leave A1 fixed. And take D to be now the union of these G's in the stabilizer. Okay, so in this particular thing that will be D. Okay, so this will be D for future reference. And then N, the number of minima necessarily that you have to take, will be the group, the order of the group divided by the order of the stabilizer. Okay? So naturally, because you have so many. Then these are the hypotheses. These are exactly the hypotheses. Okay, now the theorem. This is our first theorem. It goes back, it's in a series of papers. There's a paper 2011 with Giorgio. Then we eventually, gradually improving the assumptions, eventually have the best assumptions. Cannot calculus of variations 2013. This was a joint paper. This is a paper by myself. This is a paper that Giorgio wrote. So this evolved eventually to the following kind of result. In the hypotheses were improved gradually. Okay, so hypothesis H1, H2, H3. There are two parts in the theorem. One part tells you there is a solution, which is equivariant, and it is also maps the fundamental domain into itself. So in some sense, it's the simplest. It's like when you do Liouville theory, Sturm-Liouville theory. It's sort of, it is the simplest solution because you minimize, and actually it's a minimal solution in the class of the equivariant class. It's slightly better than that, but let's put it like that. So the first thing is that there is a solution. There exists a U. U takes the closure into itself. Of course, it's equivariant. Okay, we don't want it trivial, so we need an estimate. The second part is an estimate. So again, we want to call it a connection. So we can think of this solution by using this picture here. So you shouldn't confuse the target and the domain and the target. So think of two copies of R2 here for simplicity. So in this case, n equals m equals 2. U is a map. Here, say, is A1, and here is A2, and here is A3. Then this solution takes the whole plane and maps it into a bounded region. And it has a property that if I take a ray here in this D1 and I go to infinity, I converge here. Any ray inside this. Take any ray inside this, I converge here. And any ray inside this, I converge here. This picture is suggestive, but we have not proved exactly this picture. But I show you this picture so you have an idea. We don't exactly know that it maps diffeomorphically this onto this in this geodesic triangle. That has not been proved. But there is a solution, so now let me write down the estimate. There is a solution which, if I restrict it, say, to D1, so the distance of the solution, so this ray thing, I want to write down something that implies that, is a certain constant, the distance of x from the boundary of D1, and it goes exponentially. And this implies exactly in particular what I just told you. At this point, the theorem doesn't tell you anything about what happens if instead of having a ray, I just go tangents, I go in parallel to the walls. I don't tell you anything yet about this, but we will be discussing. You understand? This is not covered by the theorem. You have to be inside in order to get information. So this is the first theorem I would like to discuss, and let me give some information about the history of the theorem. The first important results in this direction were, there was a paper by Bronsard, Gui, and Satzman, and that was the equilateral case, the equilateral on the plane. So that was a paper in 1996 in the Communications in Pure and Applied Math. And that is the case m equals n equals 2. And this is for the group of the equilateral triangle. And then much later, there is a paper by Gui and Satzman. It is much later, it's 2008 in the Indiana, where they did the tetrahedral case, the tetrahedral group. And then our theorem is kind of abstract, doesn't require the geometry of the group. That was our contribution. Because their theorem is very complicated, as you get to different groups, they had to construct the solution by hand by starting from lower dimensional objects and building it, while we just construct the solution and then we analyze it down. So these are very important things because they started this, plus these are the two important cones. Okay? These are the two important cones. The solution is a minimality property, but at this level all we know, even for these cones we are talking about, that it has minimality in the equivariance class, but the omega where you restrict does not have to be symmetric. So it suggests already that there's something that you can try to prove minimality in general, but that we don't know. Okay, so let me see. Let me say that, let me write this with capital letters, open. The problem is open, existence is open without symmetry. I know many people that have tried it. It's a difficult problem, and I will indicate why. It's a difficult problem if you don't have symmetry to construct a non-trivial solution that connects at infinity the minima. Okay. So the next thing, let's go to density estimates. So the other blackboard is completely disappears. Oh, I can do this. We will never see it. So density estimates. What we mean by that? Okay, now assumptions. Let's take a W, very general W, has a minimum, and then otherwise it can do very crazy things. That's our W, this is our M. No symmetry, nothing. The symmetry was just there for that particular, and if I need it later I will tell you. But we look at this. Assume that A is isolated, and say this is the distance from the rest of the zero set of A, from the distance from the rest of the zero set of W. So A is isolated, you have to keep this in mind, and therefore this excludes immediately the case of the connected target. In the case of the connected zero set, immediately, because it's not disconnected, it's not isolated there. So this is a fundamental hypothesis and refers therefore to the phase transition situation only. Our hypothesis, H1, W non-negative, W C alpha. By the way, the more singular the potential, the easier the result, the easier the proof of the result. C2 is much harder, the proof, but that's all you need, C alpha. A isolated in the zero set of W. Hypothesis 2, take a D and think of that D as an example. So take the U, which goes from D to Rm, U minimal. And as we said, but I'm emphasizing it, bounded. I think we need bounded from the beginning. Okay, now we have theorem 2. So theorem 2. This is a theorem in 2015. It's going to appear in this issue that Baldinozzi is, you know the issue probably. Many people here that have contributed to this issue, so it's going to appear there. For every lambda, positive, but less than that distance. For every mu, positive. If the measure of the unit ball, which is in D, so let me not now, right, because the notation will get, is more than lambda, that this measure is more than mu 0, then the measure is more than this, provided that the ball we are talking about is in D. Okay? Provided the ball is in D, you have this density estimate.
Excuse me, do you have a direct definition of the boundary of the So it's a minimizer?
It's a you assume you have a minimal solution. Nothing.
Is there a non-degeneracy condition on the size of the...
There is what?
I mean, does W have to increase at some speed at the origin?
No, the solutions are bounded. The solutions are bounded. So you don't care about the behavior of W at infinity because solutions are bounded. Eh?
At the point A.
No. Yeah. This is a very good. Thank you. Of course. So of course. So it is as the picture suggests, and this is an important hypothesis. So if it was C2, say non-degenerate. If it is Helder, then Helder non-degenerate. So take it to be C2, so I don't have to write down carefully the assumption, and assume in the C2 case that A is non-degenerate. So let me assume, and that's a very important hypothesis, that I forgot. So A non-degenerate. Yeah, thank you for this. Thank you very much. Okay, now let me say that this theorem was proved in the scalar case in a paper by Caffarelli and Cordova. They have written 2 papers. This paper, so for m equals 1, this is Caffarelli Cordova, and they proved in 1995, and that is the case, the scalar case. Now there are people that have extended this, like people like Savin and Baldinozzi, also Matteo Novaga with Muratov. They have, there are people in the meantime that they have thought about the Caffarelli Cordova result. This, in the vector case, is our contribution to try to do it in the vector case. And let me let me suggest how this can be used, at least in the context of what I have been discussing. So a way to use this, let me give an indication. For example, remember that for existence, we have to take these balls, go to infinity, and then minimize over the balls, want to take the limit non-trivial. So take a d to be like this. And you have this estimate, which is not compatible with the basic estimate, that you have the upper bound that is like r to the n minus 1. So unless you converge very quickly to A, then you will contradict with this the upper bound. So for example, suppose I am in D and I can take balls. I have a sequence that goes to infinity where I know that I am bounded. I have the following hypothesis. I know that the distance of U from the rest of the zero set, so the distance, so the infimum in D is bounded. Suppose I know this in D. So in D, I am secure from the other minima for some reason. Then, and suppose by contradiction, there is a sequence that goes to infinity that I am bounded away from A1, from A. And then you realize then I can get increasingly larger and larger balls where the estimate holds and I'm still in D, and this will contradict the upper bound, which the basic upper bound. So this tells you that there is a certain distance away from which you have to be very close to that. But now look why symmetry is very important and very convenient. Because how do I exclude that I am close to the other minima? Symmetry excludes that. If I have two minima, it's not a problem, because if I am away from the one, I will be close to the other. If I have three, I may be missing always one of the three, and that is a problem. That's why the triple junction problem is difficult. So this gives you a sense. Now you realize that one can get the various corollaries of that, and I have to optimize what I will tell you. So I may have to skip some of the things that I was intending. So let me see where I am. What did I do with my? Yeah. Okay. Now, for example, easy corollaries. Not trivial, but easy. For example, by using the relative isoperimetric inequality, you can say something about the boundary, and therefore you will get a sharp lower bound. So for non-trivial minimizers, you will get this sharp lower bound. Remember, there's the upper bound, the corresponding thing. This is not the right upper bound for the Giesecke-Landau potential that vanishes on S1. So you get this. So another thing, if you look at the epsilon, the blow-down thing, you will get uniform convergence of the level sets. Actually, that was the original motivation of Caffarelli-Cordova, to get uniform convergence of the level sets and strengthen considerably this very weak convergence, L1 log convergence that gamma convergence gives you, which is very difficult to use in order to get further information for the minimizer. So let me only indicate that, let me write it like that. So if you look at the level sets, now I am in the new variables, then I look the level sets, the right quantity is the modulus. You don't want to mess I mean, the modulus is good enough to get information, and you take gamma small, depending on the distance from the other minima, then this thing converges uniformly. Okay, so it converges uniformly to the level set. So you get this kind of consequences and get Liouville theorems, you get things like that. So now let me tell you something which is also conceptually new, because this is, I think, more important than try to derive certain consequence states, certain consequences. So in the vector case, you have the cones have a hierarchical structure. So you have just a moment. You have a stratification of the cones. So let's think of a cone. Let's think of the cone, and in the scalar case, you just have a plane. Now, let's take this cone. And think of this cone in R3. What we have proved with this theorem, say? You prove that if you are inside one of the three domains that is of the partition, you go to A1, A2, A3. But so across the plane, however, well, let me put it this way. Let me also do the cone in 2 dimensions, which is simpler. So in 2 dimensions, you prove that if you go like this, you go to an equilibrium solution, a trivial solution, a 0-dimensional solution. Now you would like to say something if you go in this direction. Then there you expect that you should go to a connection that connects this to this. So suppose I have this point A1, I have this point A2, and I have this point A3. So similarly here, you have, it's richer. If you go in this direction, you want to show that in that variable you will converge to a 2-dimensional solution, like a triple junction solution. If you go parallel, of course, to a plane, you want to go to a connection, 1-dimensional connection. And then also you want the kind of Liouville theorems now you want before would be of the type you coincide with the trivial solution A. Now you coincide with a solution which has fewer variables than you started with. So this is the kind of context that you have, which it doesn't exist in the scalar case. So let me very schematically, let me state a theorem. Let me state a theorem. So in other words, you have the following abstraction of the density result. Now you are thinking of your function u as, so you have 2 variables. Say you have the variable x and you have the variable y. Suppose the variable x is in R, and suppose the variable y is in Rn minus 1. So just think of the simplest possible thing. If we go in this direction or in that direction, you go to one minimum or the other. So the simplest possible thing to explain the result would be 2 minima. If I go like this, I go to A plus. If I go to A minus. But now I want to say something about going in this direction. So I'm thinking now of this as living in a Banach space, and now I'm comparing u with a solution, a connection, a 1-dimensional connection, and I want to show that instead of going to A, that was a 0-dimensional solution, I go to a 1-dimensional solution. So this is abstraction. This is exactly the abstraction you want to do in order to be able to prove a result, a hierarchy result, a stratification result like that. Now, so far we have been able to give a theorem in the symmetry class. So whatever I tell you is restricted to symmetric solutions. This is where we have to do, we were able to do it. So let me quickly state the result. So you have an effective potential now, which is measures, is a functional, is not a function, is an effective potential. So you could call this the effective potential. And this measures the difference of the actions with a connection. E is a connection. Think of this, suppose you have a connection like this. So suppose here I have my A minus, and suppose here I have my A plus. Therefore, think of a connection as being like this, symmetric. So I'm assuming symmetry, I told you. We are not completely general. And now, instead of the usual norm, you will have the L2 norm in order to compare with the connection. So hypothesis, U from Rn to Rm. And we needed more than 3 here for some reason, technical, it's not important, I think. Take lambda star, there exists a lambda star, which is like a number, and we assume certain things about the connection, being about its spectrum, certain things. So which this lambda star is related to the isolation of the connection if you look at the potential from that point of view, in analogy to what we were discussing. So there exists a lambda star such that for every lambda which is between 0 and lambda star, and now you are not looking at balls, but you are looking at cylinders that are centered around the y0. The behavior here has already been proved with the previous theorem that you converge exponentially. So this dimension is irrelevant. And so you are looking at balls like this that are interested. So cylinders now are the important things, not balls. So if you know, therefore, that now this is the ball centered here, you go with respect to the second variable, think of this as being your y. You know that the unit ball, that this is more than mu 0, then that was wrong, my apologies. That this is now this, of course. Then you will get that this I'm under pressure, that's why I'm not doing very well. Okay, so of course I have to do this. I am inside here, yeah. And I want this to be more than mu 0, then the corresponding thing will be like this. And so also the fundamental estimate in this case, let me finish by writing this, the fundamental estimate over the cylinder, so I will finish exactly with this, is what you would expect, because we have now higher codimension. So we have higher codimension. So the basic estimate in this context is like you are in a R cylinder centered at y0. Okay, so this is okay, we have this. And now we subtract the action. So let's write this. So the corresponding estimate here that you get, and this is how everything begins, now is this. Okay, I went a little bit too fast. I want to thank you for your patience and your attention. Thank you.